Okay, let's dive right into this. We really need to talk about the hidden limits of today's most powerful AI models. I mean, we see these massive language models doing absolutely incredible things, but we've kind of bought into a myth that just making them bigger and bigger will eventually make them smarter. Well, according to a really fascinating paper by Anindya Mishra, that whole approach might just be a dead end.
And this right here gets to the heart of the paradox, doesn't it? We have AIs that can whip up breathtaking art or write some seriously sophisticated poetry, but then they can turn around and just completely fail at tasks that require, deep, multi-step reasoning. How can something be so brilliant and yet so fragile at the exact same time? It turns out this isn't some bug that needs to be fixed. It's actually a core feature of their design.
So, first up, let's really unpack this contradiction. The source material calls it the AI genius paradox, and it's the absolute key to understanding why our current approach to building AI might have a very, very hard ceiling. And let's be super clear here. These failures aren't just, little hiccups or gaps in their training data that we can just patch up later. The paper argues that these are structural failures. These models fail predictably and they fail consistently on problems that require thinking things through over many, many steps. Why? Because the reason they fail is built right into their DNA.
Okay, so this brings us to the diagnosis of the problem, the limits of what the paper calls a monolithic model. Now, this is the main design for pretty much all of today's big AI, and getting our heads around its built-in ceiling is, well, it's critical.
So what exactly is a monolith? Okay, imagine a brilliant but very stressed out chef. You tell the chef they have exactly 5 minutes and one fixed tray of ingredients to create any dish someone asks for. Doesn't matter if it's a simple salad or a super complex multi-course meal. That is a monolithic AI. It gets one shot, one single forward pass with a fixed amount of brain power to solve whatever you throw at it. And this slide, it just lays out the core problem perfectly. Some problems, like, say, planning a complicated trip or solving a tough math proof, they just don't fit into that 5-minute window. Their complexity can grow and grow almost infinitely, but the model's computational budget, that stays fixed. So when the task gets bigger than the budget, failure isn't just possible, it's pretty much a mathematical guarantee. And this is the line from the paper that should really stop all of us in our tracks. We can't just throw more data at this. We can't just train a slightly bigger model and hope the problem magically disappears. The source argues this is a hard limit, something that's baked right into the mathematics of how these models even think. It is a ceiling, and we can't break through it just by scaling up. Now, you might be thinking, hey, what about all those clever prompting tricks like chain of thought, where you ask the AI to think step by step? Well, the paper talks about this directly. And look, those tricks are clever, for sure, but they don't change the underlying mechanics. Going back to our chef analogy, it's like giving the chef a longer, more detailed recipe, but you're not giving them any more time in the kitchen. It's still one single shot with a very fixed computational boundary. So if this monolithic single-brain approach is a dead end for really complex reasoning, then what's the alternative? This is where the paper pivots to a really cool solution, moving from a single mind to what it calls a society of AI minds.
And this right here gives us a blueprint for that new way of thinking. Instead of one giant brain trying to do everything all at once, we're looking at a modular system. Think of it like a team of specialized components, each with its own specific job, all working together to solve the problem. It's a completely fundamental shift in how we build these things.
Let's break this down with our kitchen analogy because it works so well. The execution layer, that's your team of specialist chefs. You've got one for sauces, one for pastries, one for the grill. The control layer is the head chef, the one who breaks down the big, complex order and assigns all the tasks. The memory layer is the kitchen's pantry and all its notebooks, a persistent place to store ingredients and what's been done so far. And crucially, the verification layer, that's like an external food critic who comes in and checks each component to make sure it's correct and up to standard.
So this new setup, it doesn't just work differently. It allows for a whole new way of solving problems. It's not about getting it perfect in one shot. It's all about a cycle. Think, check, and repeat. This comparison just makes the difference so clear. A monolith takes a single shot with a limited amount of computation, and it's really prone to making stuff up, hallucinating, because it has no way to ground itself in facts. But the modular system, it uses an iterative process. It builds up computation over time, and because it has that external verification layer, it can actually fact-check its own work, which slashes the number of errors. So let's just walk through how this actually works. A complex problem comes in.
The control layer, our head chef, breaks it down into smaller, manageable pieces. It sends the math part to the math model, the text part to the text model. Then, the verification layer checks the outputs. Is this right? Does it make sense? The results get stored in memory, and then the system can loop back, building on its own previous work, until the entire problem is solved. It can literally think again.
And this is a profoundly important idea from the paper. Instead of needing an infinitely powerful brain that can just think harder and harder, this system uses memory to store its progress. It basically converts a problem of computational time, which remember is limited in a monolith, into a problem of storage space, which is way, way easier to scale. This is what unlocks that kind of long-term planning that's just impossible for a single-shot model. So what does this all mean for the future of AI? Well, the paper argues that we really need to stop looking for a single, giant, monolithic savior and start thinking more like systems engineers. I mean, this is such a powerful statement. None of the individual pieces, not the math model, not the text model, not the controller, none of them are an artificial general intelligence. But that true, robust intelligence, it emerges from the interaction between all these specialized parts. Intelligence in this view is a property of the system as a whole.
So the really crucial point is this. The race to AGI might not be won by whoever builds the single biggest model. It might actually be won by the team that designs the most effective architecture. The source suggests the mathematical limits don't block AGI, but our current design choices do. The future isn't about more brute force. It's about a more elegant design.
And I think this final quote from the paper's conclusion just perfectly sums up the entire argument. The goal isn't to build a model that gets everything right on the very first try. The goal is to build a system that has the humility and the capability to check its own work, correct its own mistakes, and try again. That iterative, self-correcting loop, that is where true intelligence might actually live.
And that leaves us with a pretty fascinating and kind of huge final question to think about. If intelligence isn't a monolith, but a system of interacting parts, what other complex problems are we trying to solve with the wrong architecture? What else are we building wrong?